Saturn is far stranger than most people realize. We all recognize it as the solar system's showpiece, that golden gas giant wrapped in stunning rings. But beneath that beautiful exterior lies something violent and powerful, something completely hidden from our view here on Earth. That's exactly why NASA launched a spacecraft called Cassini back in the late 1990s. It was an incredibly ambitious mission that ended in the most dramatic way possible. And the discoveries it made will completely reshape how you think about this planet. Here's something most people don't realize. Saturn's rings are vanishing. In cosmic terms, they're remarkably young, formed roughly 100 million years ago, and they're already fading away. One of the most compelling theories about their origin goes like this. Long before the rings existed, Saturn had an additional moon. It wasn't particularly large, maybe 400 kilometers across, but it was an extremely dense sphere of pure ice, and it was orbiting dangerously close to the planet. Over an immense stretch of time, Saturn's gravity dragged this moon closer and closer until it crossed a critical boundary called the Roche limit. This is the threshold where the planet's gravitational pull overwhelms the moon's ability to hold itself together. Imagine two forces locked in a tug of war. The icy moon fighting to stay intact while Saturn pulls it apart from every direction. Once that line was crossed, there was no going back. Saturn's gravity shattered the moon, fracturing it into countless fragments and scattering roughly 17,000 trillion tons of ice into orbit. All of that debris began swirling around the planet, pieces smashing into each other, grinding down into smaller and smaller chunks, pulverized into dust, and flattened into a thin disk by the planet's rotation. So those iconic rings? Saturn had to tear apart one of its own moons and wear the remains like a crown. Today, most of the material in the rings ranges from about 1 centimeter to 1 meter across. But the full spectrum includes everything from microscopic dust grains to ice boulders tens of meters wide. The physics behind ring formation is essentially the same process that builds solar systems and galaxies, just compressed into a much smaller scale and a much shorter timeline. The entire disk of ice around Saturn likely took shape in just a matter of days. What's particularly fascinating is how a uniform disk transformed into the distinct banded structure we recognize today. When the original moon broke apart, a handful of larger fragments survived. These chunks got trapped inside the swirling disk along with everything else. Over time, they settled into stable orbits and began circling through the debris field, sweeping up dust and ice particles along their path, essentially carving highways through the disk. These are called shepherd moons, and the lanes they cleared are what gave Saturn's rings their distinctive pattern of bright bands separated by dark gaps. The dimensions are staggering. The rings extend over 280,000 kilometers from edge to edge, nearly enough to bridge the gap between the Earth and the Moon. Yet their average thickness is only about 10 meters, roughly the height of a 3-story building. If you approached Saturn from the side, the rings would be virtually invisible. From a distance, they appear flat and featureless, but up close they reveal an incredibly complex 3-dimensional landscape. Some sections ripple into waves, sculpted by the competing gravity of nearby shepherd moons. Others have built up towering ridges of debris with peaks reaching 200 meters high. We know all of this because of Cassini, arguably the most ambitious planetary exploration mission ever undertaken. It was a collaboration between NASA, the European Space Agency, and the Italian Space Agency. The spacecraft launched in 1997, spent 7 years crossing the solar system, and then devoted another 13 years to studying Saturn and its surroundings. Nearly everything we understand about Saturn today traces back to Cassini. The probe flew directly through the rings, sampled the space between them, and ultimately plunged into the planet's atmosphere. But more on that ending later. Here's the thing, we are extraordinarily fortunate to exist at a time when Saturn still has its rings. The very same forces that created them are now steadily erasing them. Saturn's gravity constantly tugs ring material downward toward the planet. That's one mechanism of destruction. But the shepherd moons contribute as well. Some have accumulated enough mass to gravitationally attract surrounding dust and debris, like tiny cosmic vacuum cleaners, growing heavier and pulling in even more material. Others are too small for gravitational capture but still collect particles simply by plowing through them, like a snowball rolling downhill. Whatever dust the shepherd moons can't absorb, they tend to push away, either down into Saturn's gravitational embrace or outward into the void. The longer this goes on, the thinner the rings become, until eventually they'll be gone entirely. Unless, of course, the shepherds themselves eventually spiral inward, get ripped apart by the Roche limit, and restart the entire cycle. Here's something surprising. Saturn's largest ring is nearly invisible to the naked eye. It's an enormous bluish halo extending far beyond the main ring system, visible only when sunlight strikes it at just the right angle. This ring wasn't born from a destroyed moon. It's being actively generated right now by a very much alive moon called Enceladus. Scientists had long known Enceladus was an ice-covered world orbiting just beyond the main rings. But when Cassini arrived at Saturn in 2004, its instruments detected something unexpected. The radio signals coming from Enceladus were irregular and inconsistent, not at all what you'd expect from a simple frozen sphere. Mission controllers decided to redirect the probe for a closer look. What Cassini found was astonishing. Enormous geysers of water vapor erupting from cracks near Enceladus's south pole. That faint blue halo around Saturn is literally a ring of water being sprayed into space by one of its own moons. But the rings aren't even the strangest thing about Saturn. Zoom in on the planet itself, and you'll find mysteries that run much deeper. Like this, Saturn's North Pole is home to a storm system shaped into a nearly perfect hexagon. This vortex is wider than the entire Earth. It was first glimpsed by Voyager 1 in the early 1980s, but wasn't studied in detail until Cassini got a close look in 2013. It remains one of the most baffling phenomena in our solar system. Keep in mind, there's no solid ground on a planet like this. It's layer upon layer of gas compressed into thick clouds. Inside those clouds rage violent storms with thunder, lightning, and ferocious winds. Saturn has the second fastest wind speeds in the solar system, trailing only Neptune, with gusts clocking in at 1,800 kilometers per hour. You can see the evidence in the massive cloud bands wrapped around the planet, racing at tremendous speed, sometimes flowing in completely opposite directions. And right at the top sits one dominant hurricane that has captured hundreds of smaller storms in its orbit. Surrounding all of it is a polar jet stream that acts as a six-sided wall, sealing the polar vortex off from the rest of the atmosphere. The baffling part is that nobody can fully explain it. Every other naturally occurring shape in the solar system tends toward circles and spheres. This is the exception. Researchers have attempted to recreate the hexagonal storm pattern in laboratory settings using rotating fluid tanks. Certain flow conditions can briefly produce a hexagonal shape, but no experiment has ever generated a stable, persistent hexagon like the one on Saturn. The current leading theory suggests that the visible storm in the cloud layer is being driven by something enormous happening deep within Saturn's interior. To understand this, you need to appreciate how gas giants are structured. They're not entirely gaseous, but they're not solid either. Think of them as a gradient, a smooth transition between different states of matter, getting stranger the deeper you go. Saturn's composition is deceptively simple, about 3/4 hydrogen and 1/4 helium. This makes Saturn remarkably light for its size, so light, in fact, that it would be the only planet in our solar system capable of floating in water, if you could somehow find an ocean large enough. But Saturn is still enormous. That sheer bulk creates a gravitational field powerful enough to compress hydrogen toward the core until gas transitions into liquid. Below that ocean of liquid hydrogen sits an incredibly dense core of rock and metal. The crushing pressure heats this core to around 11,000 degrees Celsius, more than twice the temperature of the sun's surface. Coming back to the hexagon, the leading idea is that a powerful vortex deep in the liquid hydrogen layer, something like a massive whirlpool over the North Pole, is driving the storm system we observe from space. Why such a vortex would exist in the first place remains unclear, but its rotational energy could be generating clusters of storms that rise through the atmospheric layers and merge into that single geometric shape. Replicating these conditions in any laboratory is essentially impossible. You'd need superheated, ultradense liquid under crushing pressure on one end and the frozen vacuum of space on the other. There's another curious detail: the hexagon changes color. In Cassini's 2013 images, it appeared distinctly blue. By 2017, it had shifted to gold. The prevailing explanation is that color tracks the planet's seasons. Blue during winter, gold during summer. Unfortunately, we never got to see whether it turned blue again, because 2017 was also the year Cassini's mission came to an end. But what an ending it was! After 13 years orbiting Saturn, the probe was nearly out of fuel. NASA's team faced two choices: switch to a low-power conservation mode and let the spacecraft drift uselessly, or go out with the most spectacular finale imaginable. They chose the finale. The plan was to spend Cassini's remaining fuel on a controlled dive into the planet itself. Everyone knew the probe wouldn't survive long. Atmospheric winds would eventually overpower its thrusters, send it tumbling, and Saturn's immense gravity would do the rest. So to squeeze every last bit of science from the mission, engineers designed a carefully plotted series of orbits, each one bringing the spacecraft progressively closer to the point of no return. The first set, 20 passes, took Cassini through the outer fringes of the rings, skimming through the swirling field of crushed ice. Then came the grand finale. The probe dove into the narrow gap between the planet and the innermost rings. With every orbit, it descended a little further into the atmosphere. On the 22nd pass, it was over. The thrusters lost their battle against the winds in the upper cloud layer. The spacecraft began to tumble. Contact with Earth was severed. The screens at mission control went dark. Cassini would have spiraled downward for some time before being torn to pieces, its fragments crushed and ultimately melted in the planet's deep atmosphere. Those final transmissions from Cassini will be our last close-up view of Saturn for a very long time. There are proposed mission concepts aimed at returning to the rings and atmosphere sometime later this century, but none have solidified into an approved plan yet. In the meantime, the mountains of data Cassini gathered are still being analyzed and interpreted by scientists around the world. The investigation is far from finished, and some of the most profound discoveries may still be waiting in that data. Cassini was just one of many probes humanity has sent outward, each one searching for answers to the solar system's greatest mysteries. What hides beneath the clouds of Venus? What lurks under the great red spot of Jupiter? Those are stories for another time.